Okay, this is a worked example of a mechanics problem. This is actually from an NXL AS level paper, and this is a sort of fairly um, typical kind of problem that we might get in AS level, and essentially because the level of content, and obviously I haven't covered the year 13 content at that point. So really, it's a sort of a kind of synoptic problem involving forces and kinematics. So you're liable to see this, and this is at the sort of the kind of one of the kind of harder problems, if you like, in an AS mechanics paper. Okay, so let's have a look at the problem. Um, right. Well, so what we've got here is we've got two balls connected by a string over a pulley, and as usual, I've got to move the assumptions up here to the left here. I can just get my pointer going. Balls are modelled as particles. String is modelled as being light and inextensible. Always make those. Being light means that we've got the same tension applied throughout of it, and extensible means that, of course, it's not subject to kind of stretching, which changes the calculations. A smooth pulley, and air resistance is negligible. Right, okay, and so here we go. It's all described here. We've got a mass of 2m at the end of P, 5m at the end of Q. It starts off at rest with them hanging freely. And we've also got these distances. I think as soon as you see weights and distances, then you got to suspect there's going to be both forces and kinematics involved in this. And the system is released from rest. Okay. In the subsequent motion, Q does not rebound when it hits the ground. P does not hit the pulley. So we're actually looking at the sort of the period of time when this is traveling sort of down to here, and it doesn't kind of just stops dead. Um, all right. So the first part of the question up here, using this model, write down an equation of motion for P. So, so we're using Newton's second law of motion for this. So what I've done here, I've denoted the tension in the string as being T, and it's equal in both directions, and we've got an acceleration of A. So if using those values there, then when we're looking at P, which is going to travel upwards, I think we can see intuitively there as the T is going to go upwards. The tension minus the downward force, which is 2m times gravitational constant G, is equal to 2ma, which is equal to the mass 2m times the acceleration. And then we've got a similar thing for Q, but being downwards 5mg minus T is equal to 5ma. Okay. Um, so those are the equations of motion. I think I would argue actually that equations of motion should really be kinematics equations, not related to force and mass. But I think seems to be a pretty moot point. So if you are asked for an equation of motion, you need to keep an open mind as to what the examiner's actually looking for. Then find in terms of h only the height above ground at which P first comes to instantaneous rest. Right, so we've got to try and imagine what's happening here. Is Q's descending and it's accelerating as it descends. And of course, because these are connected particles, that means that P is accelerating up with the same rate. And this is something that's common to connected particles in general, is the thing that ties the things together. Apart from literally, is the acceleration. They share the same acceleration. So So that will happen. So it accelerate, but when Q hits the ground, then there is no down, there is no force pulling P upwards. It will continue to travel upwards, but of course it's now decelerating because because of the acceleration due to gravity. Or it's actually deceleration due to gravity, isn't it? And so it will continue until the velocity is zero. Okay, so it's got an acceleration phase, um, which has got distance through a distance of h, and then it's got a deceleration phase. Um, well, we're trying to find really, I mean, we know where it starts and we know the acceleration phase. So really, the challenge is to find the distance it travels in the deceleration phase. Okay, so I mean, this is now a kinematics problem, and we're only going to be able to solve this really if we actually know what the acceleration um, is, um, the initial acceleration. So I think that's probably maybe intuitively the first thing that you need to go for here. Right. So what we're going to do is look at the whole system. This takes T out of the equation, and this is normal for systems of particles, connected particles, we might say, is that when we're looking at all the particles together, we're not actually interested in the interconnecting forces, which is very often tension in connecting strings. So we're looking at the total net force on this system. Well, the total net force, of course, Q is the weight of Q is pulling that way. The weight of M is pulling that way as well. So the net force is going to be 5 mg minus 2 mg. Um, However, the mass it is the mass of the system, and so that's so we're adding 5m to 2m to get the total mass times the acceleration. Right, okay, now cm is going to come out of that, and if we're taking g as being 9.8, which is typical in is a sort of default value in at Excel examinations, then we've just got an equation there in A, which is going to bring A to be 3/7 g of 4.2 in actual fact. Right, so that's the acceleration. So if we know the acceleration, we can now work out the velocity that at which it is traveling when P is traveling upwards when Q hits the deck. Okay, well, it's obviously the velocity of Q as well. But it's P that we're interested in. So P accelerates at 4.2 meters per second for a distance of h. So what have we got? We've got the acceleration, we've got the displacement equals distance in this case. The initial velocity is zero because it's released from rest. What is the final velocity? So we're going to use this formula, which kind of is sort of intuitive from there, isn't it? Equals that, and that. So that basically, when we plug our values into there, is going to give us 8.4h. So v is actually square root of 8.4 h. But we actually need to know v as such. We need to know v squared. So just keep that as v squared there. So either of those two might come in the next stage. Right, so now we're into the deceleration phase. Okay, and now in this situation, of course, it's the acceleration due to gravity. There are no other forces involved. The initial velocity for this phase is what we finished with last time. Okay, so that's u squared is 8.4 h. The final velocity, well, this is when it's instantaneously at rest, when of course it's reached the top of its travel, and that's going to be v equals 0, and it's s that we are trying to find. Okay, let me just scroll down a little bit. Okay, so again, we're using this kinematics Suvat equation. And when we plug those values into there, you can see that actually we've got an equation in S, well, and in H as well, but we're actually asked to find the solution in terms of H. So that's going to give us S equals this lot, which in turn is 3H by 7. Okay, so that is the height, the distance it moves during the deceleration phase. So if we add all those together, that's the height at which it starts. That is the acceleration phase, which is just h, because that's the distance that q travels to get to the ground, and then this deceleration phase. And add all those up together, and we get 24h by 7. Okay, so see, I was hedging my bets whether we're going to be working in fractions or decimals here, but it sort of comes out best in as a fraction, I think. Okay, so that is the total height. So kind of quite a good problem, really. I broke my old rule here. I always say draw your own diagram and populate it with information from the question. I haven't done that on this occasion, actually, because first of all, in the forces sense, this is a fairly simple diagram, and secondly, I just wanted to fit it all on one page, so it's easier to put onto the video. Right, there are another couple of parts to the question. State one limitation of modeling the balls as particles that could affect your answer to part B. Well, this is a sort of fairly standard kind of question, and the point is, of course, that perhaps the clue really comes from this. It's got the height of the center of the ball here, isn't it? As h. So in actual fact, when q hits the ground, it's actually travelled h minus its own radius, right? Now, if h was to actually be just the distance to the bottom of the ball, then that's going to affect the other calculations, the forces and affect this height here as well. So basically, that's why we model it as a particle, because it makes all these measurements sort of fairly straightforward and AS level friendly. But of course, in reality, it wouldn't be that. So yeah, so that's one assumption that affects the answer. In reality, the string will not be inextensible. State how this would affect the acceleration of the particles. Well, yeah, I mean, essentially, when this hits the ground, you're going to get some elastic effect coming into it. So it's not going to perform as it would in terms of this model. So basically, that is it. So yeah, quite a good problem. Nice mix of forces and kinematics. In actual fact, neither the forces aspect or the kinematics aspect is that difficult. I think really the key to this is really just sort of visualizing what the system is going to do, and so I think that's the kind of learning point from this kind of problem, is just to try and understand how the particle or particles are going to perform, and likely is not going to have to break it down in a similar way to this if you get a similar problem. Okay, so that's basically it. So thanks for listening.